Kaka'aka Waterfront Park. Kaka'aka Waterfront Park is this. Let me see if I can look it up on the internet. Kaka'aka Waterfront Park. It's an epic park, and I used to go there as a kid whenever I would go down. And let me see. Kaka'ako. Okay, wait. Google's kind of figuring itself out. There we go. Kaka'ako Kaka'ako Waterfront Park. Okay, there we go. All right, Google Maps. There's Kaka'ako Waterfront Park. It's kind of right off Ala Moana. Here's Ala Moana Boulevard. Um, Waikiki's kind of in this area. Kaka'ako Waterfront Park is kind of this hidden park. It's really cool though. In fact, actually, I think it was right there, right about there, right about here. Let me see if I can recognize this area. Okay, there we go. Pulling it, pulling it, pulling it. There we go. Right about here. See, you can't really tell from this map. Yeah, you can't zoom in anymore, but you can't tell from this map. But this map has these epic hills. There we go. Kaka'ako Waterfront Park. Oh, plenty of people got married there. But, alright, here we go. This possibly could be a good picture right here. So, my favorite thing about Kaka'ako Waterfront Park when I was a kid was actually these hills that it has. And what you would do is you would go on there as a little kid and you would slide on these cardboard boxes. You know, I really got to make a video of that one day because I think it'd just be epic. But anyway, here's my question for you. I was kind of solving this thing and I was kind of trying to figure out what is your acceleration? Oh, whoa. There we go. Come on, paint. It says not responding, so we're going to have to wait a second for it to respond. What is your acceleration that you have? A equals what? If you are going down this incline plane. Alright, so here's how we kind of do it. First thing we do is if we have an incline plane, what we're going to have is angle theta. Alright, first thing I want to do is talk about the forces. What forces are on here? And I know that they have their own problems, so let's kind of like, whoop. Alright, let's say, how much do you weigh? Well, let's say you weigh 200 pounds. I think that would be more like how much do I weigh? So the weight is equal to 200 pounds. And the coefficient of friction, there's definitely friction in between here and the grass. The idea is to try to get it as small as possible, but you can't say that there is none. So let's call it, I don't know, 0.5. That's a lot of friction. I'm not sure if that's exactly how much friction between grass and cardboard is, but you know, we'll see. Okay, so what forces are acting on this sucker? Let's do those in red. All right, the forces that I see is the force of gravity. We call that the weight, which is 200 pounds. Another force that I see is the normal force. The normal force pushes up perpendicular to the incline of the plane. It wouldn't push directly up because if you look at how is the ground pushing on the box, well, it's kind of pushing in this first direction. So that doesn't make sense to make it go directly up. It would actually be going perpendicular to the plane. And we'll call that FF, force of friction. And the last one is oops, I gave you the hint for the next one. This is the force N, which we also know as the normal force. And the last one is force F. We call that the force of friction. Cool? Alright, now what we're going to do is, here's the thing that makes it a little bit tricky, is this. This is at angle theta, and this is also kind of at angle theta. And the direction of motion, the thing is moving in that direction. It's accelerating down, kind of at an angle as well. So if we call our standard coordinate system, you know, the positive x, positive y, The problem that we're going to run into, the trouble that we are going to have, is this: um, we're going to have to break a whole bunch of stuff into its components. We're going to have to break this one into its components, this one, and this one into its components. The only vector that we have going in that one particular direction is it's going straight down. So we'll have to break everything else into its components. That's not fun. So what we would rather do is break as little as into its components as we possibly can. And the trick to doing that is this. I can't really show you on the computer screen, so maybe I can just ask you to turn your head. Turn your head a little bit to the sideways, and what you'll see is if you do that, you can make your coordinate system kind of like this. Kind of like how back in projectile motion, when we didn't call everything in the going up to be the positive direction, in some cases we called down to be the positive direction because things were generally moving down. Kind of a similar case here. Things are generally moving down and to the left, so we're going to call down and to the left the positive direction. And see what that does is it aligns this vector here and this vector here and this direction of motion here with the coordinate system. The only thing that is not in the coordinate system is the W. So that means we have to now break only one thing into its components, and we can leave the rest of them. All right, so how do we break this into its components? I don't see a triangle. Well, you would if you kind of extend out, because remember the y direction kind of goes this way, right? And the x direction kind of goes this way. Do you see a triangle now? Looks kind of like this. If you're any good at geometry, you could figure out that if this were theta, then technically this is theta as well. I'll show it to you, or actually, you know what? I'm going to ask you to prove it to yourself. Prove that to yourself. But for now, know that those are theta. So if that's theta and that's theta, then, okay, so this is W. Let's go about doing it this way. This is using SOHCAHTOA. This is W cosine theta. And this is W sine theta. If you don't believe me, oh, by the way, this is Wx, and this is Wy, which is equal to W cosine theta and W sine theta. If you don't believe me, use SOHCAHTOA and figure it out for yourself. Now, the trippy thing about this is this. Usually, when we do these problems, usually the y direction is the W sine theta, and usually the x direction is the W cosine theta. But the reason why it's different this time is because usually the angle is down here. But in this particular case, we're measuring the angle from the top. So therefore, you're going to have a different trig functions, because essentially if the angle were down here, then this side would be the opposite. But now the angle's up here, this side is now the adjacent side. And whenever you're dealing with adjacent, you're dealing with cosine. Are we cool with that? Well, there's no one else out here, so I'm going to say, yes, Mr. Dalton, we're cool. All right, so essentially, instead of taking this red W, what I did was I broke it up into its two components, Wx and Wy. So instead of seeing this red force of gravity, think of it as these two orange arrows. All right, so if we want to add up the forces, what we're going to have to do is we're going to have to look in both directions. And in order to figure out what is the acceleration, let's go with the x direction. Force of acceleration, or sum of the forces in the x direction is equal to mass times acceleration in the x direction. Notice how I spoke that whole thing out. The sum of the forces, if I add up all the forces in the x direction, it's equal to mass times acceleration in the x direction. The question I have here is there an acceleration? And the answer is, if it's not zero, then the answer is yes. And it's not zero. I can't tell you for sure that it's zero. So therefore, I have to say that let's keep it. If I add up all the forces in the x direction, the two ones that I see is Wx, which is in the positive direction because positive is going to the bottom and to the left. And I also see minus force of friction. Now, and it's equal to mass times acceleration in the x direction. All right. Wx is W sine theta, And we learned earlier that the force of friction is actually a secret code for mu times the force normal. And that's equal to mass times acceleration in the x direction. Now, we would be done with this. The problem is we don't know what this is, and we don't know what this is. Question mark, question mark. So we got to kind of say, okay, fine. If we don't know what those are, and we were looking for the AX, right? Then essentially, in order to figure out what Fn is, we should go to the other direction. Let's do it. Adding up all the forces in the y direction is equal to mass times acceleration in the y direction. Now, first thing I ask you is this block, or are you on top of your cardboard accelerating in the y direction? Are you going up and down in this direction? The answer is no, because you're moving only in this direction, which we call the x direction. You're not moving in the y direction according to our coordinate system. So this acceleration is 0. Let's add up all the forces in the y directions. The one I see is force normal and the weight. Okay, so it's plus Fn minus Wy equals 0. So the left side is this, the right side is 0, because 0 times m is still 0. And essentially you're telling me that Fn equals Wy, which tells me Fn equals W cosine theta. So now I can take this Fn, plug it into there, and my answer that I end up getting is this. W sine theta minus mu times W cosine theta is equal to mass times acceleration in the x direction. And what I should do is I need to solve for ax, so I should kill both sides with m. Alright, so my answer is ax equals W sine theta minus mu times W cosine theta all over m. Alright, now that is your answer. I don't know, you just plug stuff in. So what is it, 200 times the sine of, I forgot to tell you what 30 theta was, let's say it's 30 degrees. 200 times the sine of 30 minus 0.5 times 200 times the cosine of 30, all divided by, well, whatever your mass is. And if I give you two, and I hate working in pounds because mass becomes weird in pounds. If you figure out what mass is in pounds, it's if your weight is equal to mg, then your mass is really just W over g. So whatever that is over g. You guys want to see something really interesting? Okay, this is my answer. But do you want to see something just that would trip me out? And here's what here's the thing that just I look at it and just be like, wow, that's really cool. Is this W is equal to mass times gravity, right? So mass times gravity times sine theta minus mu times mg cosine theta all divided by m. If I cancel out m, cancel out m, cancel out m, I can cancel out m. I think that that's so crazy. Ax equals, I'm going to factor out g because there's g's in both of them, g times sine theta minus mu cosine theta. Now that's really cool. That tells me that the mass doesn't matter. That tells me that the weight doesn't matter. There's no weight in this equation. That's actually my answer, the most simplified version. But there's no weight. That just blows my mind. Now the reason why it blows my mind is this, because if I'm challenging my son, and my son is 7 years old, and so he doesn't weigh like 50 pounds, and I weigh almost 170, something, really heavy. I challenge my son to slide down this hill. Who will accelerate faster? And the answer is neither of us. Neither of us will accelerate faster. We will both accelerate at g times the sine of theta minus mu times the cosine of theta. That's crazy. Now here's my question to you. Why is that?